Thank you, everyone. My next lecture, and it's a good timing that I talk just right after Nicholas. So, yeah. So I hope the memory is still fresh. So, yeah, Nicholas gave me a few more tests. So more tests. So I added a few slides. So hopefully, let's see how it goes. Okay. Yeah. So first, acknowledge everyone again. So I'll just skip that. Okay, so first, that's the original title. I'm going to briefly review the two spiral grouping symmetries, mainly the U4 symmetries, which you guys already talked about, and a little bit about the ground states. And then I'll move on to excitations. Basically, how do we solve the excitations exactly in certain limits, and basically how do we see the ghost modes, and I'll talk a little bit about the generic understanding of the ghost modes in condensed matter physics, and also the charge 2 excitations. Actually, Andrew mentioned a little bit, and again, this is the topic I didn't finish last time. If I have time, I'll move on to that part. Okay. Yeah, so this, again, we've seen this many times. Basically, there's an experimental finding that you observe a rich phase diagram as function fitting and temperature, of course. You have the superconducting phases, and basically the superconducting phases sits at non-integer fittings in between the integers, and all the insulating phases are located at integer fittings in the integer number of electrons per unit cell. And here we use fitting nu from -4 to +4. Of course, you can consider ±4 as well as the filling relative to the charge neutrality. Okay. Yeah, seen this, and you've also seen this. This is just a single particle model of this spiral grouping, and here we have the two important parameters. Yeah, basically only two tuning parameters in the model, which are the AA hopping and AD hopping. And these two, in general, due to relaxations, the velocity is smaller than W1. And for, as Nicholas mentioned, for the actual magic angle to spiral B, W0 is about 0.8 times W1. And again, we have the 4-4 degeneracy from 2 spins and 2 valleys for the Bloodband. So in total, we have 8 Bloodbands. Okay, and Nicholas has mentioned that now if we move on to interactions, so the interactions, the dominant interaction in this system is basically Coulomb interaction. But in general, in the experimental setup, basically we have the gates, bottom gate and top gate, which can be understood as metal plates. So if you remember the electromagnetic theories you studied, so basically the metallic gates would give you some screenings. It attracts basically screening charges. So your interaction, Coulomb interaction, is a screened interaction with a range of E, which is typically 10 nanometers in transport experiments. Okay, so that's the interactions we are going to take. And as Nicholas already introduced, basically when you project the interaction into the 8 Bloodbands, this is your Newtonian. Basically, you can rewrite it as a semi-definite form, which is basically this O minus Q minus G is the dagger of OQG. So it's something O dagger O, which is non-negative. And this operator O is basically the projected density operator. So here, basically electron density, the bilinear density operator, times the form factor from the projections. Basically, when you do the projections, you will get some factors from the wave functions. And this coefficient, because V here is Coulomb interaction, which is always positive, you can take a square root. It's still a real number, so this O is a Hermitian. Sorry, it's not Hermitian, but basically this number is real, and you can make a Hermitian operator from O dagger O, which is non-negative. And as Nicholas said, So with a non-negative Hamiltonian, the advantage is if you can find a state with exactly zero random value, then it's exactly a ground state of this HI. And this Hamiltonian, just by looking at the Hamiltonian here, it has a U2 times U2 symmetry, where each U2 is from the spin and charge rotation in each valley. And basically here, the rotations, if you look at carefully, this O orbiter here, it's summation over all the spin and valley is eta. So basically this total when you sum over them, yeah, actually the matrix element field depends on eta, as you see here. So it's not rotationally invariant about the valley rotation, but it's invariant about spin rotations and of course the U1 charge rotation. So this is the symmetry you have for this interacting Hamiltonian. Okay, yeah, basically as Nicholas mentions, these flat bands, earlier we showed it has a Wilson loop like this. It can be actually basically if you choose a different basis for these two bands in each spin and valley, you can write them into a term basis, which EY, where EY here is plus minus 1, which is giving you the term number of this band. Here, yeah, you use the unconventional notation EY because, yeah, in some sense this is a yeah, this is the eigenvalue of the sigma Y Pauli matrix in the original entity band basis here. Anyway, okay, so here the way to define this term base is pretty easy. Basically, you just first you need to fix the phase vector in front of your eigenstates. So if this is the creation operator in band n, and you put plus minus 1 for conduction and valence band, and eta, and that's our valley and spin index. If you fix the phase of this wave function by the C2VT symmetry, then you can simply define your term bases in this way. And you can prove actually they give you the term number plus 1 and minus 1 bands. And it's intuitively you can understand this from the Wilson loop. So basically, one of the eigenvalues of the Wilson loop goes from minus pi to plus pi, which is similar to a term number plus 1 band, and the other eigenvalue goes like this, which is like a term number minus 1 band. So this indicates you can always decompose the basis into term number plus 1 and minus 1. Okay, and these term bases are not eigenstates, of course, as we know. The energy eigenstates are C orbiters here. But if you take the flat band limits, basically you just assume the bands are perfectly flat, then conduction band and valence band have the same energy, and then you can do any superposition of these two bands, which will still give you eigenstates. So basically in the flat band limits, the term bases become your single particle eigenbases as well. Okay, the nice property of the term basis is it's the most straightforward way to understand these U4 symmetries. Of course, you can prove these U4 symmetries more rigorously by considering the symmetries I'll mention briefly later. But basically, if you don't ask about the derivations, so this is the result. So basically, if you take a flat band limit where you ignore the kinetic energy, because I told you the reasonings. So here's the result. So you will have a enhanced symmetry. The symmetry is enhanced from U2 cross U2, the spin valley rotations, into U4 symmetry. And this U4 symmetry would allow you to rotate do any rotation between the spins and valleys. Yeah, but actually I should say that this rotation in the valley space it's not a straightforward rotation. So it's rotated. Basically, you rotate the spin and valley, the two bands in the spin and valley, in a kind of a local way, but it's actually slightly different from for term number plus 1 and minus 1, yeah, which I'll just mention. Okay, but basically the idea is when you have the in the flat band, when you're in the flat band limits, you have additional local symmetry, which is remember that this P is particle symmetry, it flips the energy. So the single particle energy. So you have to have this single particle energy approximately 0 to allow you to have this symmetry. Your Hamiltonian is invariant under the symmetry. And if you look at the our earlier definition, actually P also flips R. C to Z doesn't flip R. Sorry, C to Z also flips R. So the combination of the two is a local operator. It's and it's actually important to have a local operator when you generalize. When you want to get some enhanced continuous symmetry, right? Because if it's continuous symmetry, it's actually a continuous local symmetry. So you want to always find some local operator. And with this additional operator, you can see that you immediately enlarge your group into U4. And in the super Cairo flat limits, where if you make the AA hopping to 0, then you have actually a further enhanced symmetry, which is U4 cross U4. Here, the additional symmetry operator is this Cairo symmetry C. Again, it anti-commutes with Hamiltonian, the single particle Hamiltonian, so you have to use the flat limit. But then it's also a local operator. And here, these two U4s are pretty intuitive. So the first U4 is just rotating any rotations among the 4 Chern number plus 1 bands, and the second U4 is any rotation within the 4 Chern number minus 1 band. Okay. Yes.
So why is the Cairo limit important for the U4?
Yeah, because you want to have an additional.
Oh, so the C one.
Yeah, C is for that now equals to 0. Okay. Yeah. So in the Cairo flat limits, again, this will be my entire component because I don't have kinetic energy anymore. So if I want to solve in ground states, I just need to find the ground states of the direction component. And the nice thing about this term basis it's not intuitive, but basically it requires you to do some calculations. But basically, when you write this interaction operator OQG, it's actually a bilinear operator. You can show this bilinear operator here in the Cairo limit. If you make the assumption it's Cairo, but now equal to 0, this basis, this interaction would be, this operator would be diagonally in the term basis. So it's only hopping electron. Actually, it's diagonally term basis and valley and spin. So basically, every band only hops within itself in the term basis. That's only true in the term basis. Okay. Yeah, where this coefficient is in general a complex number. Okay. So basically with this operator hopping only within each term band, so it's easy to get the ground states, which are basically you can fully occupy any integer number of these term bands, or leaving all the other bands fully empty. Because when you have fully empty or fully occupied band, then these operators, Q is non-zero, it hops in 2 different momentum states. If this band is fully occupied, then you cannot do any hopping. So basically, this operator acting on the state will give you 0. And similarly for the empty state. So basically, when you fully occupy integer number bands, you get a exact eigenstate of this Hamiltonian. And as Nicholas mentioned, actually, under the condition of support of flat band limit, the flat metric condition, you can show these eigenstates are exact ground states. And here, because you are allowed to occupy any number of the term bands, your total Chern number actually can vary within some range. For getting nu, here nu plus and nu minus is representing the number of Chern number plus 1 bands and number minus 1 bands to occupy. Your Chern number can take these values, obviously. Okay. Yeah, so basically that means in this Cairo flat limit, at each fitting, you could have multiple degenerate Chern insulators. Okay. Yeah, so there's, I think we already talked about it. Okay, anyway, so here, this is just more mathematical. So basically, we said that OQG acting on the state will all be 0 because you can't do any hopping. But when Q is 0, actually, you can get a non-zero result. So there your automatic is given by this number, which you can calculate. And this number, basically this number would be a constant under the supermetric condition. So it's just equivalent to a chemical potential in that case. So you can, if you shift your chemical potential, you can make this say a ground state, which is basically what you do experimentally. And because we have the U4 cross U4 symmetry, if all the ground states have a huge ground state degeneracy manifold, so you can do any U4 rotations, U4 cross U4 rotations. So they are, if you regard them as pseudo spin degrees freedom, basically you can treat them as ferromagnets, the U4 cross U4 spin. Yeah, so I guess you guys talk about something about the representations of the U4 cross U4 and how it's given out. Basically, if you have finite number of electrons, you can actually count how many states you have by looking at the representations. Okay, so some general understanding why do we have a ferromagnetic state here? Actually, I think I mentioned it's a few days earlier when I answered someone's question. So basically, recall that in insulators in Hubbard model, they actually have anti-ferromagnetic states. But here, it's usually more conventional if you have a topological band. Your ground state would be more preferring ferromagnetic states instead of anti-ferromagnetic states. That's basically because you have topological states. Basically, that means your Wannier function is kind of delocalized, and as a result, your interaction becomes somewhat non-local, because if you take the Wannier basis. So if your interaction is non-local, kind of non-local, or it extends to some range, then ferromagnetic state will save you the energy, because if you have ferromagnetic states, your wave function also, so basically the spins are polarized in the same direction. So your orbital wave functions would be between two neighboring sites would be basically anti-symmetric, and this would save some overlap between two different sites, and saves your the Coulomb energy. And similarly, basically in quantum Hall physics, you also have the spin ferromagnets because of the topology of the term band. Okay, so yeah, so all these are chiral-flat limits, which give you actually many degenerate ground states, which is obviously not true realistically because we are not in the chiral-flat limit. So if you take the non-chiral-flat limit, basically by making this W naught no longer zero, that's closer to the physical reality. So what you have is this O operator is no longer diagonal in the term basis. So you get additional contribution, this O1, which is a hopping between different opposite numbers within each spin and valley. Okay. This number, of course, you can treat this part as a perturbation, but this breaks down somewhere when W naught is as high as 0.8, for example. So that's why you guys actually talked about we need Hartree-Fock, etc., other methods to determine the ground state. But assume W naught is small enough, then the perturbation theory will work. Then basically this O1 term, if you're occupying one of the term bands and leaving the other empty in the same spin and valley, then this O1 acting on this state will give you some non-zero contributions. And it turns out, so this contribution would be positive because it's O dagger O. Basically, whenever you have this O operator acting on it non-zero, it gives you some positive contributions. Yeah, but actually, the story is slightly more complicated. You also have the crossing term between O naught and O1, which gives you a negative contribution here. That's the negative number here, the U2 term here. But if numerically you find this entire number here is always positive. So basically that means if you have a half occupied spin valley, it give you some energy penalties. So basically you want to then when you choose which bands to occupy, you want to occupy fully occupy as many spin valley flavors as possible. But when you fully occupy spin valley, this gives you total to number 0. So as a result, basically you get a energy penalty proportional to your turn number. So this is why you prefer a lowest number ground state actually in the non-chiral limit. But here you still have the U4 symmetry. So this ground state here is still a U4 fragment. And yeah, actually this ground state is still exact when if you're considering the filling to be even, which gives you a 2-number 0 state. Because in that case, this whole one is completely 0 acting on the state. Okay. So further, if you include the perturbation of the kinetic energy, the effect of the kinetic energy is basically fixing the polarizations in the valley space, because the valley, earlier we said actually the valley rotation for the valley rotation to be symmetry, you require the kinetic energy to be 0, because you want the particle and chiral symmetry to become part of the symmetries. But basically, this calculation is very tedious. But basically, it gives you some energies as a function of the valley polarization angles of these term bases. So here recall that we have U4 in the chiral flat limits. We have U4 symmetry in the term number +1 basis space, and another U4 in term number -1 space. So each of them can have different valley polarizations, represented by the arrows of 2 colors. So basically, by these energy calculations, you can show sometimes they like the valley polarization to be polarized in K or K prime, which is valley polarized state, or they could prefer a state like this, which is incline. Incline blocks here of the valley state, means equal superposition between K and K prime. So here, this is just a summary of the results. So these dashed lines represent the intervalley coherence. Yes, so this is called intervalley coherence when your arrow is even. So this represents the intervalley coherence basis, while the dotted lines are the valley polarized basis. So this is the ground state. Basically, at odd fittings, for example, in this case, at -3, your state is actually preferred to be a valley polarized state, while at even fittings, at all the even fittings, you actually prefer to occupy the intervalley coherent basis. But this is actually the so-called KIVC state. Here, the K actually also have a mini. If you look at the 2 bases, basically the coherence, the signs, the coefficient here are different, are opposite for term number +1 and -1 bases, and that's so-called K. Basically, for these 2 coherent bases have a sign dependence on the term numbers of the bases. Okay, and experimentally, as you probably know, at 0 magnetic fields, we don't see many Chern insulators. It's probably only in 1 or 2 samples. Yeah, that's basically because the perturbation theory could break down when W0 is too far away from 0, and which is roughly the case in reality. But when you add a magnetic field, you can actually stabilize these Chern insulators. And the generic understanding is basically, here we are just providing a zeroth order understanding, which is actually there are still subtleties. But basically the rough understanding is you probably learned about the strata formula from earlier talks. Basically, when you have a non-zero number, when you add a magnetic field, the number of electrons occupied in the state would change. It would change by this amount proportional to number times magnetic field. And this is similar to the lambda level. When you increase the magnetic field, your number of lambda level degeneracy increases. And with this additional number, and if you have a chemical potential here defined relative to the Chern neutrality, then you would have a free energy change in terms of this number. So basically, actually, because your state is repulsive, for positive fitting, mu is positive. So basically, that gives you negative. Basically, your state with a larger delta can be favored when your away from zero magnetic field. And by that, you can actually estimate, basically, for example, at turn number at U2, at some magnetic fields, the turn number +2 stay would win by the in the free energy, and you can estimate what's roughly the transition magnetic field. So basically, these states, all these states at higher magnetic fields are seen experimentally. For example, first in Arias group, and also in several other groups, both SEM and transport. For example, there's the data from AFCO's group in transport. So all these slopes here represent the highest number states of high magnetic fields. And if you interestingly, actually, if you look at this experiment, this is actually an earlier experiment in AFCO's group, they see a hysteresis loop here for u to the -1 or +1. Yeah, +1 probably, which actually corresponds to, we believe, roughly reflects this first order transition here, and it's a non-zero magnetic field, so which is natural because it's a two number 1 to 3 transition. But of course, in reality, they don't see perfect quantizations, so it's not a perfect transition signature. But if you look at the magnetic field, about 1 Tesla, which is of the same magnitude we estimated. Okay, with that, I should switch to charge excitations. Mostly, I was assuming Nicholas is talking about the first part, so mainly talking about the second part. Okay, so we mentioned already, we have exact ground states in the chiral flat limit, which are basically fully occupying integer number of term bands. Okay. So here, if you recall my definition, so D are the operators for the term bases. So basically, when I write C is the operator for energy band bases. Here, D is the term band bases. So this actually Andrew and Nicholas already mentioned this, so it's relatively probably familiar to you already. So basically, when we mentioned earlier, the ground state set by this condition, if you want OQG with Q non-zero acting on the state, it gives you 0, and it has some eigenvalue at Q equals 0. Okay, with this property, basically if you regard this part as a proper chemical potential, which you can subtract. So basically this means if you consider a state which is D dagger, any of the D dagger within these empty states acting on your ground state, so that basically just creates one more electron in the empty band. Then this state, the energy of this state actually is easy to calculate. This is because basically when you look at the commutator of this OQG with D dagger, the commutation of them is still an operator D dagger because OQG is basically a bilinear operator. Okay, so basically this means when you add the Hamiltonian onto the charge excitation, it still gives you a charge excitation state. So when you look at this entire HI commuting with D dagger, basically this means you're calculating the energy difference between the charge excitation and the ground state. When you look at this commutator, actually HI actually conserves momentum. So as a result, you get the same momentum, the same momentum with this coefficient here. Actually, in the chiral flat limit, it's pretty easy because because the Hamiltonian preserves the term number, your excitation is still in the same term bands and the same spin and value. So it's exactly the same state. Actually, you already get your eigenvalue. You find this already eigenstate with the coefficient you can calculate. So here, for reference, this is the expression for the charge excitation eigenvalue, which you can actually calculate without doing any diagonalizations numerically or anything. So you just count. Of course, you first need to know the wave functions from single particle Hamiltonians, but then you just use those wave functions, you can find this diagonality. Okay. And similarly, basically, as long as your ground state is exact, you can take this trip. Basically, if your Hamiltonian annihilates your ground state exactly. Okay, so this is some results. Yeah, so here, yeah, I should mention that you could similarly create whole excitations by having the annihilation operator on the ground states, and you get a similar expression for the energy of the hole. So here, the blue and red lines are for the electron and whole excitations, and yeah, in a momentum space. Basically, this momentum is the momentum of the excitations. And here are some results. So here, this is new to zero, zero filling. Zero filling actually because of particle symmetry, because you assume graphene has particle symmetry. The electron and hole excitations overlap. So basically, there are two lines that are overlapping. Yeah, so this is what you get in a chiral flat limit. Yeah, here we always assume flat band limit. Okay, so in this case, you just have many degenerate excitations. They are all degenerate. They have the degenerate expression. So when you break the chiral symmetry, actually you develop two different energy bands within each spin and valley. So basically, this is how it changes. But one thing to note is that as you're going away from the chiral limit, your depth actually decreases. But at nu to the zero, this is not very serious. But at nu to the minus 2, basically at nu to the minus 2, your energy distributions will become asymmetric between electrons and holes. And in this case, the effect of non-chiral perturbation actually significantly suppresses your gap. For example, at nu to the minus 2, it's almost already close to zero when you're at minus 2 filling. Actually, if you go to nu to minus 3, it gives you a negative gap. Basically, that means it becomes a metallic phase there already. Yeah, that's the case where your flat metric condition is actually strongly broken. Okay, so here, this result is in chiral flat limit where you still have finite depth. Okay, so but more intuitive before that. Okay, before, yes, go ahead.
High symmetry point, we are still digit.
Sorry?
At high symmetry point, we are still 2 full digits. Even
yeah, very good point. So like here, you could say that these degeneracies are protected by C3 the symmetries. Of course, this depends on what representations they are in. At K point, was basically the same thing as Dirac, the Dirac protection. The gamma point is trickier. So basically, you can show the Hamiltonian, the interaction Hamiltonian has a higher symmetry there, so they give you a degeneracy. But when you include kinetic energy, the degeneracy of the gamma breaks. Because we know there's no degeneracy at gamma points. Okay. Yeah. So one question is: are these excitations the lowest charge excitations? Right. So we are considering charge 1 plus minus 1 excitations. But here, actually, you can also have this is the so-called trion excitations, right? So you can create 2 electrons in 1 hole. Of course, if they are not bounded together, they are not called trions. But basically, there's all kinds of possibilities you can have. You can have furthermore 3 electrons in 2 holes. So, so the nice thing here, you know, that is the space of 1 electron is just closed within itself. This is no longer true when you go to higher excitations. But here, what they do is, yeah, you can truncate your Hamiltonian Hilbert space up to excitations of 2 electrons and 1 hole, for example. In principle, you can do higher truncations, but that will give you an even larger Hilbert space. So within our numerical calculability in diagonalization, we just truncate to these 2 kinds of excitations. And within this Hilbert space, you can show, yeah, this is basically the result. This is the actually the excitation. Yeah, n+1 means the ground state has n electrons, and you just add one more electrons to your system. So this is the energy difference between the generic excitation and the lowest excitation there. So you see the 0 here actually means the lowest excitation. So here, as you can see, in most cases, here probably, yeah, we can only do the kind of Bloodband because of the limitation of the Hilbert space. But anyway, you see that this E dagger psi is almost always already the lowest excitation as function of psi. So the psi is giving. It's indeed the lowest charge excitation. Except in this case, it's the only case we find it's not the lowest excitation. So you have kind of this kind of excitation, which is giving you the lowest excitation at this stage. Okay. Yeah, but anyway, that shows this is a good approximation for the lowest excitation. Even in this case, it's not a big difference. Okay. So more intuitively, these charge excitations actually exactly correspond to the Hartree-Fock band structure, which we already mentioned. So the relation is as follows. So before that, let me just briefly recall what the generic Hartree-Fock theory for interaction, four-hormone interaction. So basically, our Hamiltonian, if you rewrite everything in terms of the Fermi operators, so here I'm just doing a simplified version, ignoring all the term numbers, spin, and value indices. But in general, our Hamiltonian has a form like this, and we chose this operator to be not normal order to make it nice looking, and actually, it's easy for us to control the symmetry about charge neutrality. So basically, these O operators are the density operator minus 1/2, which give you a shift symmetric about the charge neutrality. Okay, if this is your Hamiltonian, then the Hartree-Fock theory is basically contracting into the contractible operators, assuming they give you some mean field value, and then you will end up with a bilinear Hamiltonian, which is free Hamiltonian in that. Okay, so basically the Hartree term just has to come from the contraction between these two operators and these two operators. You have two waves, so you get a factor 2 again, which cancels the factor 1/2 here. So this is a Hartree term, which is basically from the density. It's called basically the density term. It gives you a potential from the electron density. And you also have contractions between this C dagger here and C here, which give you a Fock term. But you get these 1/2 vectors because we include these 1/2 vectors. And this is actually important for ensuring the symmetry about charge neutrality. Yeah, so basically this is called the exchange term or the Fock term. So if you assume these take some values, then you get Hartree-Fock Hamiltonian. But in the case that our ground state is exact, if we know that all these bilinear operators acting on the state give us either 0 or some constant value. So basically that tells you these expectation values are actually exact. They are not the approximate expectation value. So for these exact ground states, then your Hartree-Fock theory actually becomes exact. So these numbers are exact numbers, and you can actually find an exact Hartree-Fock Hamiltonian. And this exact Hartree-Fock Hamiltonian, if you do the calculation, it's exactly the same as the charge neutral. Yeah, this are not the charge excitation, the energy of charge excitations we found earlier, except that you need to flip the whole energies, which is natural because now you're considering everything in the electron picture. So if you basically flip the dispersion of the holes into electrons, this is the Hartree-Fock band structure, which you can somehow think of it as the effective band structure of the system, right? And as we earlier said, actually because you're away from the chiral limit, when you go away from the chiral limit, your energy gap actually shrinks. So although this big energy scale between the two bands is about 25 MeV is given by the Coulomb energy scale of the Coulomb interaction. This effect of non-chiral actually give you a big deformation around down point, which make your gap actually pretty small. And that kind of explains why experimentally, so in STM, you can detect this 25 MeV energy scale roughly between the peak of the density space between two bands. But in transport, your energy gap is actually as small as 1 MeV. It's really into this big deformation. And actually for Newton -3, for example, this deformation could even give you gapless band structure. That's why in many cases, at certain fittings, you don't actually see easily. Okay, and the other thing is, for example, for the new smaller than 0, which is here, obviously your hole excitations are have a smaller mass, and the electron excitations is almost flat in flat dispersion, so the mass there is very big. So when your mass is small, and you look at the Landau levels of these electrons, the Landau level spacing in energy would be larger, so that can be resolved experimentally. While you're on this side, the effective mass is huge. It's very difficult to resolve the Landau levels even in the free case. So this kind of will give you a picture why experimentally we only detect the Landau bands away from the charge neutrality, basically always in this direction. For new smaller than 0, these Landau levels are basically the Landau levels of the electrons here, which is because they have a smaller mass. Okay, make sense so far?
Sorry.
Yes.
Could you also do the same thing for the method for 0? Because 0, 0, the kind of the exact kind of limit.
For -0.
I mean, this one is a 0.8, right? The ratio is.
Yeah.
So for the case of the 0, which is the kind of.
Yeah, it's the same in the Cairo case. Actually, I didn't believe the whole energy is here, but so this is u to the -2, SW not equal to 0. If you flip the whole energy, so the dispersion upward, so basically both bands have a dispersion upward, so the whole excitations are still lighter than the electron excitations.
What is gapless?
Why is it gapless? Where is gapless?
The electron hole that.
In this case?
Yes.
It's because your Hamiltonian is it's basically the same for different numbers. Basically, those two bands come from the same spin valley. Because you have two bands there, of course, you should get two bands. But if you in the Cairo flat limit, this expression is independent of the Chen number because those two are just related by time orders. Okay, so now we move on to the charge neutrality. The charge neutral excitation. Again, so there are multiple ways of making charge neutral excitations. So the simplest way is to create one electron and one hole, but at different momentum, so they give you non-zero momentum excitation. And actually, this is also mentioned earlier by Andre. Okay? So basically, what you find is you can do the same thing to look at the energy of this charge neutral excitation. Now, of course, the calculation is more complicated, but basically what this Hamiltonian does is because this Hamiltonian conserves the momentum. Yes. Oh, okay. Oh, you mean runs over electricity or something? Oh, it says that battery. So, or I can maybe use this mic.
Yeah, how about we use the mic and we'll.
Okay, that's easy.
Thanks for pointing this out. Theoretical physicist puts in batteries.
Right, thanks. Okay, does it work?
Yeah.
Okay. Yeah, so what this Hamiltonian does is it's still closed within the space of the electron hole excitations. But it just pushes the electron to a momentum k plus p plus q, and the whole excitation to k plus q. So the total momentum is still p. So basically, for each fixed the total momentum, the charge neutral excitations, your space is closed. And yeah, so this is again because your Hamiltonian annihilates the Hamiltonian. So with this, you can diagonalize this. So for each p, now for each p, your Hamiltonian has matrix elements between different q's. So you only have one free momentum index q. This is just like diagonalizing a single particle Hamiltonian. And you can easily do that in the space of Q, which would give you a bunch of states in each for each momentum P. Okay? But actually, when you plot the band structure, of course, the x-axis is P, is the energy of the charge neutral excitations. But because of the freedom of Q, actually for each P, you also have extensive number of states. So this would be your results. Actually, you have a continuum of the charge excitations, which is typically what you would expect if the electron hole are not bounded with each other. They are free to have their independent momentum. So you just get a continuum of energies. But there are indeed a bunch of bound states, kind of like bound states of the electron hole pairs, which are disconnected from the continuum, and you always note that there are gapless modes, and this is exactly the Goldstone mode due to the symmetry gradient, which Andrea mentioned. Okay, so so the question I'm going to focus on today is how do you basically count the number of Goldstones basically from the simple understanding of symmetry breaking. Okay, so with that, let me just briefly review what the Goldstone theorem is saying. So basically, when you have a spontaneous symmetry breaking of a continuous symmetry, in general, that gives you some gapless boson excitations. That's the theorem we all know. And this is probably a familiar example. You could have for example, U1 symmetry, and you're having a breaking of this U1 symmetry by some autoparameter, and basically this is your potential in the autoparameter space. Then your ground state will be here with the degeneracy rotating with respect to the U1 excitation, right? Yeah, so in general, for example, this U1 generator is the symmetry generator of the group that commutes with my Hamiltonian, but it will change my ground state. If I pick a ground state here, acting with operator on it, it will give you another ground state, right? So it breaks the that's why you have many ground states, which all have the same energy. Okay. So yeah, the Goldstone theorem is basically, roughly speaking, proved this way, but this is just the argument, not the proof. So what you can do is you can create. Yeah, so basically, if you act this generator uniformly in space, then it just give you another ground state, which gives you zero energy. So in general, you can modify this generator a little bit. Assuming this generator is a summation of some local operators. If you give this generator another vector e to the IKR to give it some variations in the space, then you can define a state with momentum k this way, acting this modified generator with momentum k on this state, on the ground state, one of the ground state. And this basically gives you some oscillations of the autoparameter in the space. And of course, when k goes to 0, the energy of this state just goes to the ground state energy. So that's basically why you have a gapless excitation. Right? But basically, this argument doesn't tell you how does the dispersion approach 0. And in our case here, we actually showed find it's always quadratic. This is in chiral, always in the flat band limit. These are chiral and these are non-chiral. So we actually have quadratic Goldstone mode. But in high energy physics, we know we have actually linear Goldstone modes. So actually in Condensed we can have both. And this is just probably the simplest example you will all study in solid state physics. If you consider the Heisenberg model, for example, in 1D, it has the spin SU2 rotation symmetry. But depending on the sign of this interaction J, can have an anti-paramagnetic neo state or paramagnetic state. And in these two cases, you all, basically, in both cases, you break the SU2 symmetry and you would have ghost of modes. But in the anti-paramagnetic states, you probably know the spin wave excitations are linear. So basically, if you calculate the spin wave excitations by the so-called Hosting Primkov method, which I will not talk about, you'll get a spin wave dispersion, which is J and sine K. Here, K ranges from -5 plus pi, which is the Brownian zone. And you find actually you get two modes at zero energy, one at 0, one at pi. So you get actually two linear ghost modes. So for the paramagnetic case, you do the same calculation, you get the spin wave excitations 1 minus cosine K. So in this case, you just have one quadratic mode but at 0 momentum. And this is actually very interesting. So that gives you actually leads to the generic counting rule for a number of ghost modes in condensed matter. Actually, in high energy, you always have linear ghost mode because of the relativity. It has to be relativistic because something is gapless and must have a linear dispersion. But in condensed matter, we can have any of them. So in general, the rule is as follows: if your number of broken symmetry generators is N at FB here, so simultaneous symmetry breaking, and your number of linear ghost modes is NL, and number of quadratic ghost modes is NQ, then the counting rule is like this. So basically, if I have, for example, in the Heisenberg model case, the number of broken generators are 2 generators. It's actually here. But basically, when you have a spin polarization here, the rotation about x-axis and y-axis are broken. So your sx and sy of the total spin is broken. So you have 2 broken generators. But the so basically in the paramagnetic case, you just have one quadratic mode set by this equation, and in antiparamagnetic case, you get 2 linear modes. So that's satisfied, right? So here I want to provide a basically understanding why basically kind of proof for the counting rule, if you're interested. So basically the ghost modes is that they are just fluctuations of the autoparameters. So assume you have some symmetry is unbroken and some symmetry is broken. So first we always assume your symmetry generator is kind of a local operators. So basically it's a summation of all local operators like this of this form. So like what we did earlier, we can always define an excitation by giving some fluctuating coefficients to this generator. And basically I change this generator to if this is a broken generator, I can change it to a spatially varying function, which would give me some excitations. And this coefficient phi here is basically a boson field I can take. So in general, if a Hamiltonian has symmetry group G, there will be some symmetry generators unbroken, because they are invariant acting on the ground state, and these remaining symmetry generators form a group G naught, which is called the Biao group. And and you can look at basically the coset space, which is basically has a dimension of the number of broken generators. So that tells you how many generators are broken. And in the Heisenberg model case again, so we see that SA is conserved. So SA is the little group, which is U1 group, while SX and SY are broken. We have 2 broken generators. And in general, we mentioned that for each broken generator, you can have a boson field corresponding to its fluctuations. So in general, your effective action for ghost of bosons, basically these boson fields will give you the ghost of bosons. It will be a Lagrangian of the all these boson fields, which have a total number n SSB. Okay, so then the question is, okay, so we are going to make an assumption that we have a spatial inversion symmetry, which is mostly the case. So in general, you can expand the ground state in terms of these derivatives of partial phi and partial phi. So it's not a function of phi itself, because you know that if I do a constant phi shift, it's just a changing to a different ground state. So it's only functions like this. So the spatial term, the leading spatial term is the quadratic term like this, because you want to have spatial inversion symmetry. So it's quadratic in the boson field phi. Quadratic in the gradient of boson field. So if you Fourier transform, this is of course a k-squared term. Okay, so a linear Gaussian mode has a pretty simple action, which is just the Klein-Gordon equation, like a grounding. So in order to have a linear dispersion, you have another term, which is partial t phi squared, so which will give you e squared and the Fourier transform, right? So you get e squared equal to k squared, so that gives you a linear dispersion like this. And in order to write down such an action, it's okay to just have one boson field. Basically, to just have one broken symmetry and write down linear Gaussian mode. So basically, every real field corresponding to a broken symmetry can give you a linear Gaussian mode. But for quadratic dispersion, because my term in k, the leading term is k squared of all the k squared. In order to get a quadratic dispersion in proportion to k squared, you have to have a linear impartial t term in your Lagrangian. But this would not work if you just have one boson field. So this is just a total derivative, which doesn't give you anything. So in order to get a meaningful linear partial t term, you have to at least have two boson fields. And this is the simplest way to write down such a linear term. And of course, this give you a quadratic dispersion. But also, this is actually odd under time reversal, because partial t is equal to minus partial t. So this actually indicates, in order to have a quadratic dispersion, in general, your ground state has to break time reversal some sense, or at least in a long wavelength limit. So that's kind of one way to see if you have quadratic dispersion. And actually, more generally, people can just write this phi1, phi2 in terms of a complex field. And in terms of the complex field, it's actually more familiar to many of you. So basically, it's just like a complex boson, non-relativistic boson action that would turn out in total derivative. So anyway, but recall that each real field corresponds to one broken symmetry. So that means you need basically two broken symmetries to get a quadratic Gaussian mode, which you have to break time reversal. Okay, so together, this gave me the counting rule. Okay, so with that, yeah, so basically this is actually a good example for testing this rule, because SU2 is too simple. You almost can do it without knowing the rule. But basically for this case, for example, here is the number of Gaussian modes defined in the Cairo flat limits. And you can actually do the same counting by the rules we said earlier. So these are the little groups of the different ground states of different two numbers. Yeah, let me just show one example. Of course, all these states, as we mentioned earlier, they are ferromagnetic states. So they break actually all the parameters break time reversal. So that justifies why they always give you quadratic dispersions. Of course, you can prove that as well by calculations. Yeah, look at one example. Basically, this is the -1 to number -1 states. We have basically two these bands occupied, basically two bands in the same spin value. The other bands here just half occupied for this spin value. So okay, the symmetry of the Hamiltonian is U4 cross U4, of course. If we want to find the little group of this state, it's pretty easy. Basically, because recall that each U4, the first U4 is rotating among the first the term number +1 bands, and the second U4 is rotating among term number -1 band. So for term number +1 band, I have one band occupied and three bands unoccupied. So I'm free to rotate within within the occupied bands and unoccupied bands. So that gives me invariance of the ground state of U1 rotation, which is about within this occupied band, and another U3 among these three bands. And similarly for term number -1, sorry, this should be -1. For term number -1, you get two bands occupied and two bands unoccupied, so it's a U2 cross U2. So this is your, basically your little group. And the number of generators of group UN, you know, it's n squared. So become number of broken generators. In this case, it's totally 16 plus 16 and minus the number of the ghost mode. Sorry, the number of little group generators of little group, you get 14. And if you're a quadratic dispersion, you get 7 modes, okay, which agrees with our numerical. Okay. And yeah, of course, this is another example, but I probably will just do it quickly because it's the same thing. So here, if we lift the chiral symmetry into a non-chiral case, then your group becomes symmetry group becomes U4. And in this case, you can see actually some of the ghost modes is lifted into a gap mode. And by the same counting, similar counting, this is equal to -1. And again, the example we did last slide, you can check that the little group also becomes smaller. But in this case, remember that you need to rotate the term +1 and -1 together. So basically now the little group basically has 3 components. One is rotation for fully occupied spin lines within fully occupied spin lines. And this is the rotation within half occupied spin lines. And this is the empty spin lines. So in this way, you find a little group, and you can similarly calculate the number of generators. In this case, it's 10, which gives you 5 quadratic modes. And the modes are not always linear, not always quadratic. So finally, when you go to the non-chiral non-flat case, you only have the symmetry U2 cross U2. In this case, it's more complicated because the ground states are more complicated, as I earlier mentioned. So here I'll just give you a different example. This is the U2 -2, term number 0 ground state, which is the so-called PINC state, which is basically the term +1 and -1 occupy intervallic coherent basis like this. And in this case, this is the same thing as non-chiral flat counting we did earlier. The result will give you 6 broken generators, which correspond to 3 quadratic ghost modes. But if you count the non-chiral non-flat case, actually here, just a little bit. Let me just quickly do the counting. So here you're occupying only the spin up bands. So you're free to do any of the spin down U1 rotations. So that gives you 2 U1s, which are unbroken. And for the spin up, you can do a global charge U1 rotation. So that's your remaining little group. So now the dimension of the little space of little group is 3. It's odd number. So if you count number of ghost modes, the count number of broken symmetries is 5, which cannot all be quadratic, right? So in this case, actually what you have is you have 2 quadratic modes and 1 linear mode. So basically one of the quadratic mode will be lifted into a linear mode. Okay, let me just briefly mention that, this is also what Andre mentioned. So you can further calculate the charge 2 excitations by the same logic. So basically this is again a single particle problem. And this is the anti-bounding states mentioned by Andre. So basically you can get the spectrums here without problem. So one conclusion we concluded from these calculations is, actually we can also prove it mathematically, is so these calculations first, they are all at integer fillings for insulating states. But the charge excitations, the charge 2 excitations always have a positive energy. And basically here, this is the so-called charge criteria for Cooper pairing. Basically the pairing energy has to be negative for you to favor Cooper pairing. And it's intuitive, right? Basically it's the energy that you create 2 electrons minus the energy you create 2 different single particle excitations, and it's basically relative to the chemical potential. That's why I give you this expression here. But you can prove that this number is actually always non-negative, actually pretty positive. So that tells you if you want to integrate superconductivity at integer filling, Coulomb interaction plus Coulomb interaction with in the flat band limit doesn't quite work. Basically, the common Lagrange method doesn't work. Okay. Of course, we are actually limited because we only consider one kind of charge two excitations, but this is pretty much the picture. So that tells you either you need non-flat bands to get superconductivity, or you need some other pairing group, which is could be phonons. But here, yeah, let me. So first, experimentally, people add screenings. Of course, they do see superconductivity at integer fillings. So it is available at integer fillings. But on the other hand, this story is less likely because the superconductivity temperature, you know that it's the highest one. The bands is the flattest. So that means your non-flat perturbation, yeah, that's where your non-flat perturbation is smallest. So if this is the picture that non-flat band can give the superconductivity, you should expect a dip of the superconductivity when your band is the flattest, right? So this is probably indicating that you should have other pairing groups. Okay. Yeah, maybe I have 5 minutes. So that's the original plan of my talk, but now I have a part unfinished. You think that's okay? Okay. Yeah. Let me just go quickly here. About this part. Yeah, this is again going back to single particle physics, but I'd say it's very interesting, so I'll probably show it. Okay, so you'll probably, I hope you all heard about the concept of Hofstadter butterfly. Yeah, actually earlier, I guess Jonah's work was talked by Atlo, which talked about the Hofstadter butterfly. Basically, when you have a lattice, electrons in the lattice, and you add the magnetic field, you can define as flux per unit cell, right? And as basically this magnetic field would modify your band structure, and it turns out, yeah, it's modifying the band structure in a fractal way. So if you plot your energy eigenvalues as a function of the phi over phi naught, this is the Hofstadter butterfly for the traditional, the first example shown by Hofstadter, 2D square lattice. You get this nice fractal patterns. So in a small B field limit, these are just the Download level, which is kind of like the Download levels we understand, but at large fields, they break up into many more bands. In general, if the flux is a ratio number of P over Q, co-prime numbers, then an energy band will break into Q subbands. So yeah, that's basically the introduction of Hofstadter. But interesting thing is that Hofstadter butterfly have some relation with the band topology. So yeah, this is a trivial example. This model is trivial. It doesn't have topological number in the band. And here, if we look at the example of the Chern insulator model, you actually can tune the parameter to make it trivial. Both bands have to number 0, or you can tune the model into to number +1 and -1. And so the dispersion at 0 magnitude doesn't look quite different. But you note that the Hofstadter butterfly are pretty different. So in the term number 0 case, basically you can just understand the Hofstadter butterfly roughly for each band itself separately. For term number +/-1, the Hofstadter spectrum of the two bands are entangled together. Basically, they're connected in between by this spectrum. Yeah, this connectivity basically is related to the band topology of the band. And in general, actually, you can prove that the Chern gap. So basically, these two, if you have a Chern gap like this, the two energy dispersions have to be connected at this flux, basically phi over phi naught equals to 1 over c. So in this case, it's c equals 1. So, okay, so I should define as phi naught. Phi naught is actually just 2 pi in actual units. So if you add 2 pi flux in a cell, it should, in tie binding model, it should recover itself. So basically, this give you connectivity between the two bands at this flux phi equals 1. And the understanding is basically again back to the strata phenomena. And actually, in hot air backside, there's an equivalent equation called the Duventing equation, which is very similar. Yeah, so basically what happens is for each, within the gap of each hot air backside, if your flux is P and Q, actually you have 3 integer numbers associated with each Hofstadter gap. This can be proved actually rigorously. These are all integer numbers, and this number C actually exactly the Chern number we usually talk about, the Chern number of this gap. But actually, it's interesting that we have additional numbers, quantum numbers, and this formula becomes more familiar if you divide everything by Q. So then P over Q is the flux. And basically, this rho here, we can prove it actually corresponds to the number of electrons per unit cell. So now it's not an integer anymore, it's R over Q. It's a rational number for rational flux. But basically, this formula tells you, it's basically the strata formula. It tells you when your magnetic field increases, the number of electrons would also increase, which is proportional to the Chern number. Yes?
In terms of Chern number, we know that if Chern number is not zero, we can affect all the lambda levels. We'll see
Crossings for what?
crossing of the lambda. So if there is a bunch of lambda here, bunch of lambda there, there is a crossing if there is a Chern number not zero.
Oh, you mean the zero mode
Zero.
of the, yeah.
How that can be translated to the butterfly?
Yeah, very good question. So it's not quite obvious here. Actually, here it depends on the model a little bit, but basically that picture is always in a small B field limit, right? So always small B. And indeed, as you see, so if the bands are topological, you know all the lambda levels just goes upward for band bottom and downward in band top. So this mode going up here is indeed due to the zero mode you said. And it actually extends to the other bands. That's how it leads to the connection. Okay, so I'll probably skip this. Basically, it is a semi-classical picture for proving the strata formula. But yeah, let me skip this because there's lack of time. Okay, so I'll just basically tell you what the yeah. Okay. So basically, the proof of the Chern gap closing is as follows. This is basically the strata formula. For example, for 2 bands, and if you're just occupying one band, here. So this S here is the number of electrons you have at zero magnetic field. So in this case, if you're in the middle of 2 bands, you have the 1 electron occupied. And this is your density per unit cell at 35. And you will see that this rho, depending on the sign of C, of course, it will reach 0 or 2. Basically reach another integer number when your flux is 1 over C. So if you just consider a 2-band model, there will be a problem when your rho is greater than 2 because you only have 2 bands. So you can't occupy more bands. So what actually happens is this gap has to close. Yeah, basically, this for this formula to apply, the strata formula has to be applied in a gap, in a gap of the system. So the only way to avoid a problem that rho would be greater than 2 is that the gap actually closes. So that's what happens for 6 to plus minus 2. Actually, it also applies to continuum model, for example, the moiré system. This is an example of the twist double body of the so indeed, you see the Chern neutrality gap. Actually, if you calculate the Chern number, it has Chern number plus minus 2 each spin value. Okay, I'll finish. Yeah, this is my second last. Okay, so then actually you see this gap closing adds flux 1/2. And experimentally, actually, this is from the Tutel's group. Yeah, of course, there are some errors, but this is the Chern neutrality gap will be detected from as flux 5, of course, subject to some disorder effects. And you do see that this gap is decreasing out toward this 1/2 flux here, which is indicating the chart gap closing at this 1/2. And this is we argue that this is actually evidence for Chern number 2, this Chern neutrality gap. Yeah, so in general, we know like at small magnitudes, when you increase magnitudes, the gap between different lambda levels should increase. So this is really in contrast to the Euro behavior. Okay, so last slide basically for this biography, the band topology is of course different for C2ZT. Actually, Jonah has a more detailed study for C2ZT protected fragile topology, the Hofstadter butterfly there. But under certain conditions, this topology can also protect the gap closing between between the fragile topological bands and the higher bands. But it's not always actually C2ZT because of, I guess, probably because of fragility and actually the fact that magnitude breaks this time universal, it's not always the case. But it turns out that this biography model is the case, but it takes a little bit effort to understand this model, because now as a continuum model, you actually equivalent, you can think of it as a model with infinite number of orbitals per unit cell. So with that, your Hofstadter butterfly in general is no longer periodic within 2 pi, because all the orbitals are pretty close to each other. So in this limit, actually, your band structure is only periodic within minus infinity and plus infinity. Yeah, actually, if you have n atoms per unit cell, it should be minus 2 pi n to plus 2 pi n, roughly speaking. Yeah. So here you have to calculate the Hofstadter spectrum up to infinity, and yeah, actually there are different situations, but you can see that the butterfly is always definitely again at infinity. So here, yeah, this is the range of the first flat band, and it's not flat because I chose the large angle here. This is the fragile band here, and so here this is obvious. It's just connected with the higher band, and for this example here, it's actually connected at infinity. So this Hofstadter butterfly between the fragile bands and the higher bands are connected. Okay, yeah, with that, I conclude, and thanks for your patience.
Almost lunchtime. This is a great place to stop with lots of exciting things in these systems, but let's get just a few questions before we all get released.
Just a clarification, for Chen number non-zero and fragile case, with Chen number is equal to 0, what is exactly the signature from the butterfly effect? Because for both of them, it seems to have this connectivity.
No, I mean, you mean this example here?
Yes. So in the case that you have Chen number, and in case that Chen number,
yeah. So yeah, the example I earlier showed. This band is completely trivial. Yeah, it not only have Chen number 0, but also trivial many other topological numbers. In this case, it's totally disconnected, or if there are connectivity, it's not protected. So here, as we mentioned earlier, the Bloodband of 2 spider graphene are fragile topological, so it has a fragile topology there. So in that sense, although it has Chen number 0, the gap has Chen number 0, it is a topological band. And for, yeah, actually, maybe you're asking for the argument.
I'm trying to see that when I look at the spectrum of the butterfly, some of them they have Chen number 0, but they are fragile. So I want to see that.
Yeah.
What exactly is signature that I can see from the picture for fragile?
Yeah. So first we actually, for this model, we don't have a generic proof. We only have a detailed proof. Like if you really go to the 2 spider graphene model, you can show the band structure are connected. And if you, for example, if you break the C2ZT symmetry, you could get a gap here. Basically, that's a kind of indirect evidence that this connectivity is protected by C2ZT. Yeah, but that's the only thing we know, because actually for a continuum model, it's much more complicated than than tight binding model. We don't have a rigorous proof yet. But yeah, basically what we can do is to detect the connectivity.
You take the connectivity
with respect to symmetry
breaking.
breaking.
Number also is 0, then there should be a reason for that connectivity.
Yeah, yeah. Actually, you can show at infinity, it's equivalent to a monolayer graphene tight binding model in momentum space, which guarantees the gaplessness. And if you break C2ZT, of course, you can gap the graphene model there. Yeah.
Okay, then I think, let's thank Professor Biao one more time and.